again. We're still working on ice tables and what they can do for us. Here's a new thing. They're going to get a little more mathematically tricky as we go through this, so just so as you know, here we have HBr breaking down. I'm going to write this off to the side where I have a little more space to do stuff with it. So this reaction is hydrogen bromide can fall apart, releasing hydrogen and bromine. And 1 liter container, you love to see it. We're making an ice table, so we're going to have initial change and equilibrium amounts. And they tell us we had half a mole of HBr. Divide that by 1, and it's 0.5 again. That's our initial concentration. They put that in a 1 liter container, and they don't mention anything else. So we start with no hydrogen and no bromine. Time passes, and then we find that the bromine concentration is 0.130. So what happened? We want a number in the change row, and this is the obvious one. Bromine went from 0 up to 0.130, so that has to be 0.130. And now that we have this, the coefficients let us fill in the rest of this row. Hydrogen and bromine are 1 to 1, so they would both be the same number. HBr has a coefficient of 2, so it's twice as big, 0.260. And if bromine went up, hydrogen must also go up, and that means HBr must go down. 0.500 minus 0.260 leaves us with 0.240 for the HBr, and nothing plus 0.130 is 0.130. Good. It's kind of always the same sequence. Find one number in the C row, finish the rest of the C row, and then fill in what's missing after that. So there's our equilibrium state, which they didn't even want in this question, sadly. They only want the equilibrium constant. So equilibrium constant will be the products over the reactants, and the products are hydrogen, which is 0.130. The bromine's also 0.130, so I'm just going to square this because that's the same number twice. And for HBr, we have 0.240, and that gets squared because there's a coefficient of 2 on it. Remember, it's always the equilibrium numbers you're using to do this. This is an equilibrium constant. You won't get it right if you use non-equilibrium concentrations. So 0.13 divided by 0.24 and everything squared, we get 0.293 for the constant. And it looks like all the data we used had 3 sigdigs, so we really are okay to give 0.293 for our answer, unless there's something I'm not thinking of. Let's do another one. This one's kind of painful to write out, but that's okay, we're tough. Okay, so ethanol, sorry, let's get a little small. C2H5COOH, that's propanoic acid. Is in equilibrium with C2H5COO, C2H5. What is that? Ethyl propanoate and water. Dreadfully scrunched. Sorry, but the jerk who made this book, who is me, didn't give you a lot of space to work with here. Okay, 1 liter beaker, wonderful. We don't have to calculate different concentrations. They say 7.71 moles of ethanol went in here, and 7.37 of propanoic acid. And allowed to go to equilibrium, the system ends up with 4.8 moles of ethyl propanoate. 4.80. as before, they say these two things are put in the beaker and nothing else. You can assume you start with none of these species just because they weren't mentioned. So there's our starting point. What do we do first? We want a number in the C row, and the only one we have a hope at is this, 4.80. Um, this reaction's a bit dull because it's all the coefficients are ones, so that means this step goes fast. 4.80, 4.80, 4.80 again. And if this side is going up, it can't go down, it started at 0 and you can't go negative, then this side must be dropping. So nothing plus 480 makes 480. 737 minus 480 is 2.57. And 771 minus 480 is 2.91. 48571. Yeah, that should be all right. Equilibrium constant is products over reactants, so it's the two right side things over the two left side things. All the powers are 1, so that makes things easy, and we get 4.80 twice this and this over 291 and 257. Okay, 4.80 squared divided by 2.91 and divided by 2.57, I get 3.0807. All the information we were given had 3 significant digits, so we can only give 3 in our answers, so I guess 308 is where we'd have to stop. And one more. At least we have plenty of room for this one. Carbon monoxide reacts with 2 hydrogens, equilibrium, and we get methanol. Oh, this is different. Okay, they tell us the equilibrium constant. What are they doing here? If a mixture at equilibrium contains blah blah. Okay, this is actually not an ice table because they don't start with equilibrium or they don't start with initial amounts or anything like that. We have this reaction and they give us some equilibrium numbers, so I will take those. They say at equilibrium we have 0.12 moles per liter of carbon monoxide and 0.100 of hydrogen. And what is the concentration of methanol? We don't know. You can call it M for methanol or X, whatever you like. So I guess this question is to show you that not everything is an ice table. It's only an ice table if you have initial and equilibrium amounts and you can do the procedure we've been seeing before. In this one, we just have equilibrium information and we know our equilibrium constant comes from the products, CH3OH, over our reactants, which are carbon monoxide and hydrogen squared. Well, they told us the equilibrium constant is 0.5, and we know 2 of these numbers, so we can solve for the missing thing. We have CH3OH, which is X, over carbon monoxide is 0.12, hydrogen is 0.1, and it's squared. And they tell us that's our equilibrium constant, so it has to come out to 0.5. There are a lot of ways to solve this. I'm going to do one of the simpler ones that it might not be the fastest, but it's going to work. I'm going to multiply together all this stuff in the denominator. So 0.12 times 0.1 squared, and I get, so the x didn't change. Down here I get 0.0012 equals 0.5. Now, if we want x alone, right now it's divided by 0.0012. The way you get rid of that is you multiply both sides by 0.0012 because these will cancel. That'll leave x by itself, which is what we want. And 0.5 times 0.0012 gives x is 0.0006. That's a concentration, not a case, so it does have units. It's in moles per liter. All right, so ice tables are great, but don't try to solve everything with them. Some things are just about equilibrium in some way. More later, I'm sure. We'll see you there.